Everyone, we're reviewing Wetzel's Limnology textbooks. This is edition number 4, and we are focused on chapter 7, which is the fate of heat in lakes as well as rivers. And yesterday we had a general introduction about how heat is distributed through the lake. And today we'll be looking at thermal energy content heat budgets of lakes. So the thermal structure of lakes is determined by the fluxes of energy across the air-water interface, sediment, water interface, and incoming water as it mixes within the lake and the action of wind. The fluxes across the air-water interface are quantified via a surface energy budget computed from time series measurements of meteorology and water temperature. A full heat budget additionally includes discharge into and out of the system, rainfall over heat sources or sinks such as groundwater and sediments, and any geothermal heating. The extent of thermal stratification varies with heating and cooling and wind-induced mixing. A surface energy budget includes the processes that introduce heat or cause cooling at the water surface. The budget includes incoming shortwave radiation, outgoing shortwave radiation, the fraction of SWR that is lost by reflection, with their sum called the net shortwave radiation, outgoing and incoming long-wave radiation, with the sum called the net long-wave radiation, latent heat flux, which results from evaporation and leads to heat loss, or from condensation, which results in heat being gained, and sensible heat exchange, also known as conduction. These terms are predominantly sources of heating and cooling for many lakes and can be obtained with radiation measurements plus wind speed, air and surface water temperatures, and relative humidity. The terms which induce heating have a positive sign convention in this chapter. SWI, LWI, and condensation are always positive. SW0 and LW0 and evaporation are always negative, and the sign changes for SE and LE. While LWI is a large positive term, LW net is negative and contributes to cooling. Equation for the calculation have been presented, etc. The fluxes at the air-water interface are generally the largest. The fluxes at the air-water interface are largely the largest sources of heating and cooling within a lake. The surface heat energy budget is calculated as follows with the H, the net heat flux. So this is I'll let you go through this equation, and this equation basically summarizes all these terms that we looked at here. And so to determine how much heat is being added or lost over a period of time, one multiplies by surface area and time, noting that watts per meter square is equivalent to joules per meter square per second. In studies of the upper mix layer, the equation is modified to only consider the heat stored in the actively mixing layer, and the heat flux into it is called the effective heat flux. Buoyancy flux with unit of meter square per second to the minus 3, a measure of kinetic energy per unit time is computed as. So in this case, it's a third dimensional component of time. So that's kind of an acceleration based, I believe. So we have beta is equal to G alpha H over C PW rho 0, where G is the gravity, alpha is the thermal coefficient of expansion, which varies with temperature. CPW is the specific heat capacity of water, and rho 0 is the density of water at the surface. Buoyancy flux into the actively mixing layer, effective buoyancy beta star, is similarly calculated with H star instead of H. Beta quantifies the extent to which the incoming and outgoing energy will cause stratification, beta positive and mixing, beta negative in the surface layer. So let's look at this illustration that shows all the terms that we just went through here. So let's see, we have SWI, which is the incoming shortwave radiation. So SWI is right here. So this is the sun, this is the spectrum of the sun, and this is the incoming solar radiation right here. SW0 is outgoing reflected. So this is the reflected component of the solar radiation. LWI is incoming long wave radiation. So we have LWI here. And LW0 is outgoing long wave radiation, LW0. LE is the latent heat flux, LE, and SE is sensible heat flux, SE. QI is heat flux from inflows. Q0 is heat flux from outflows. So QI and then Q0 right here. QS is heat flux between the bottom sediment and water. So QS. QR is heat flux from rainfall. So QR is, let's see here, we have, I cannot see what, QR right here. Okay. And QG is heat flux from inflows and outflows of groundwater right here. Because groundwater can contribute to heat flux. I mean, it could be cooler groundwater compared to maybe warmer groundwater. Maybe it's groundwater that is warmer than this body of water because it's the groundwater that is emanating from nearby a geothermal spring, for example. And let's see, then we have U is wind speed, which acts to redistribute heat by mixing and advection associated with the energy input at the surface. The colored arrow representing the visible heating component of penetrative shortwave radiation, right here, is embedded within a larger arrow representing the non-visible component, ultraviolet and infrared component. Okay, because we have to analyze those. So I think what they're saying is like, this is a spectral shortwave radiation, the visible light, and then this is the spectral plus the spectral visible as well as the spectral invisible, because it includes UV as well and infrared. Other sources of heating or cooling include incoming and outgoing stream water, groundwater, rainwater, and heat fluxes from sediments. Typically, their contributions are minor. Sediment heating of the overlying water column can be important under ice cover. The contribution from sediment heating occurs at the sediment water interface, so it's the sediment water interface. So its contribution to the total heat flux is calculated by multiplying the flux QS by the surface area of sediment involved and the time period. Fluxes from groundwater QG usually occur in near shore or shallow water. Cold groundwater intrusions can cool lakes, and in some shallow lakes, QG can exceed latent heat fluxes for part of the summer. Fluxes from rainfall, QR, are usually variable over the surface of a lake. In the case of inflows, if the volume of incoming water is large related to the lake volume, their contribution of heat flux can be significant. The heat flux from inflows, QI, is computed as QI is equal to CPW by rho by Q, in parentheses TIN minus TW by A0 minus 1. So I'll let you review all these parameters here. And that famous volume of, so Q is the discharge, that is the volume of incoming water per second. So this is meter cube per second. And by convention in the literature, heat flux terms are identified using the letter Q, and as is discharge. Hence, we use the same letter and include the definition. The temperature of outgoing water is often assumed to be similar to that of surface water, but in reservoirs, outflow could be deeper and have a temperature significantly lower than the surface water. In tectonically active regions, geothermal heating can occur either from hot springs or from the earth's heat warming the sediments. So heat fluxes can be budgeted with these terms. Terms are assigned positive, negative values according to whether the heat flux is incoming or to the lake or outgoing from the lake, respectively. Here we use a convention that the loss terms are negative. Examples such as are provided here. Surface energy budget, net shortwave radiation is the largest source of heat. Despite LWI being a large term, LW0 is larger. Hence, LW net is negative. The depth to which shortwave radiation penetrates, enabling the water to warm and providing energy for the photosynthesis, depend on the transparency of the water. So comparison of shortwave attenuation curved line representing exponential decay with depth in a lake with low left and high optical clarity. So here we have a lake where we have pretty high clarity. So this is, I believe, meant to represent the Zeki depth and the Zeki disk. And then, so therefore, the Zeki depth is about 30 meters. After 30 meters, we cannot see the observer cannot see the disk. And then this is a lake that is highly turbid and that has a lot of CDOM, as we saw. And so then what we see is we then have like the distribution of the shortwave attenuation. So this is like the curved line right here. So from 10% to 1% over 0.3 meter, and then the same from 10% to 100%, however, over 30 meters. So this is like 100 times the depth than found here. Calculation of penetration of shortwave radiation using Beer's law was introduced in Chapter 6. Here we expand upon the formulation in Chapter 6 to include penetration for the full spectra using the symbol I for irradiance. So irradiance is equal to IO, or the integral of lambda n over lambda 1 by e to the minus k I n z over delta over by d lambda, where, and then so I'll let you go over those terms. Based on the fraction of solar radiation in each wavelength band and in attenuation coefficient, solar radiation in the visible range and that in the near infrared range are responsible for most of the heating. As illustrated in figure 7-6, the penetration of light declines exponentially with depth, and the decline is more rapid when attenuation is greater. Heating will be greater near the surface in more turbid or highly stained lake. The contribution of light in the near infrared to surface heating is greater for optically clear lakes than for turbid ones. Net shortwave radiation is zero at night and has a maxima when cloud cover is low of about 800 to 1000 watts per meter squared, with maxima depending on latitude. Heat is lost at the lake surface via several processes. Heat loss from outgoing long wave radiation can be high, up to around minus 400 watts per meter squared. Downwelling long wave radiation, LWI, from the sky is also large and larger during cloudy conditions, about 350 watts per meter squared. Thus, the net is negative. A small fraction of LWI is reflected, 3%, LWIR, and it is included in direct measurements of outgoing long wave radiation. Net long wave radiation is around 50 watts per meter squared during cloudy condition and is more negative approximately 125 watts per meter squared when skies are clear. When wind speeds are low and skies are clear, net long wave radiation can be the largest source of heat loss. Sensible heat exchange depends on the temperature difference between air and the water surface and wind speed. So before we move on, let's look at that here, this table here. So table 7-1, so wavelength bands, fraction of shortwave radiation in each wavelength band, and attenuation coefficient in each band, KIN, based on the transmission in pure water, except for ultraviolet and visible light, which may vary within the lake. Attenuation of ultraviolet radiation and visible radiation depends on chromophoric dissolved organic matter, and we just saw that here, which stains the water and particulates in the water. The attenuation in the ultraviolet K280-400 in Molo Lake was 26 to the meters to the minus 1. The attenuation coefficient of ultraviolet radiation from 280 to 350 nanometers, or UVB, in boreal lakes in the Caucasian Shield is about 3 per meter, etc. So, so then lambda, this is the range of lambda in nanometers, and this is the fraction and attenuation of -1 here, of not -1, of meter, per meter. And so it maps pretty much the range of lambda through the spectrum. All right. So we will it here. It is generally the smallest term in a surface energy budget. Sensible heat exchange depends on the temperature difference between air and the water surface and wind speed. It is generally the smallest term in surface energy budget. In smaller lakes, it may be positive during the day, indicating heating when air temperatures are higher than surface water temperatures. But it is typically negative at night, indicating that heat loss when air temperatures are cooler than surface water. On a seasonal basis, sensible heat exchange is more often positive during spring in temperate or Arctic region when lake temperatures are colder than air temperatures and can reach 100 watts per meter squared. In other seasons, and often year-round in a subtropical and tropical lakes, sensible heat loss is negative and in the order of 20 watts per meter squared. Heat is lost through evaporation, a component of latent heat flux. The rate of evaporation increases with higher temperatures, reduced water vapor pressure, lower barometric pressure, and increased wind speed, but decreases with increasing salinity. Evaporation is usually the largest source of heat loss from lakes, with values over tropical lakes during light winds of around minus 100 watts per meter squared and reaching up to 700 watts per meter squared during squalls. Evaporation is greater from warm than cold water bodies for the same wind speed. Latent heat fluxes are also higher in lakes in more arid regions with their low vapor pressure. When cold air flows over a slightly warmer lake, the water vapor condenses over the water and heat is released, contributing a slight heat input to a lake. So that will be it for today for this subchapter, and I'll see you next time.